Welcome to this explainer. You know that feeling when you're staring at a densely packed electrical engineering schematic and you just feel your heart rate instantly spike? Yeah, you're definitely not alone. But today, we're going to gently unpack the core foundational concepts of a circuit. We're not going to treat this like some intimidating, unsolvable math problem. Instead, we're looking at it as a logical, almost living system. So take a breath, settle in, and let's decode the invisible energy that literally powers our world.
Right off the bat, before we even think about looking at dense equations or those complex diagrams, let's just start with a really simple question. What actually happens inside a circuit? Think about it. When you flip a light switch, you don't actually see anything moving, right? There are no gears turning, no visible pulleys pulling, and yet massive amounts of energy are instantly transferred. To really get this, we have to look past the physical wires and understand the invisible flow happening right beneath the surface.
So here is our calm, straightforward roadmap for today. First, the invisible moving force. Second, power and energy transferred. Third, classifying circuit elements. And finally, number 4, the rules of flow. Okay, let's jump right into section 1, the invisible moving force, understanding charge, current, and potential. It all begins right here with charge. Think of charge simply as the foundational building blocks of the whole system. As our source notes define it, charge is the characteristic property of the physical particles themselves. You've got protons, which carry a positive charge, and electrons, carrying a negative charge. We measure this in a unit called coulombs. Now, charge on its own is a static concept, but get this, just lighting a standard, everyday light bulb takes quintillions of these electrons flowing every single second. Crazy, right? Let's look at how that actually happens.
Because, well, a static charge doesn't light up a room. For that, we absolutely need motion. And that brings us to current. Represented by the letter I, current is the rate of flow of that electric charge. Mathematically, our sources define it as dq over dt, which is just a fancy way of saying the change in charge over the change in time. If you think of charge as water sitting still in a reservoir, current is the steady flow of that water rushing through a pipe. We measure this flow in amperes. 1 ampere simply means exactly 1 coulomb of charge is being transferred every single second. Now, for this flow to happen, we need 2 key things. First, a defined conducting path, like copper or aluminum wire, and second, a pressure difference to actually push it along. But you have to ask, why does the current move at all? It moves purely because of the difference between point A and point B. And that pressure difference, that is what we call potential difference, or voltage. Voltage is simply that pressure. It's the invisible push that forces our charge to move and creates that current we just talked about. The formal definition from the material is the amount of work done to move a unit positive charge from one place to another. Without this voltage, without this potential difference, the charge just sits there, doing absolutely nothing. Voltage is essentially the motivation of the entire circuit. All right, moving on to section 2, power and energy transferred, the work inside the circuit. So when voltage pushes current through a circuit, work is actually being done, and the rate of that work is called electrical power, or P. The math here is elegantly simple. Power equals voltage multiplied by current, or P equals VI, and we measure it in watts. Think of power as the real-time effort of our circuit. On the flip side, we have electrical energy, represented by W. Energy is simply that power sustained over a period of time. It's calculated as power times time and measured in joules. Basically, power is how hard you're working right at this exact second, while energy is the total amount of work you've accomplished over the whole day. It's really cool to see how these concepts map together. We can track current and voltage changing simultaneously, and then, directly based on how they interact, the power output spikes up and down. Downstream from all of that, you see the energy gently building up over time. It's almost like a heartbeat tracking the effort and capacity of our system. It perfectly proves that energy doesn't just instantly appear out of nowhere, it's accumulated work. Let's step into section 3, classifying circuit elements, the organs of the system.
Instead of looking at a circuit board as a chaotic jumble of random parts, we can group network elements into really clear behavioral pairs. This makes it so much easier to predict how a circuit will act. By classifying them by their energy role, their directional behavior, or their mathematical relationship, we bring a nice logical order to the whole system. We can seamlessly categorize things as linear or nonlinear, unilateral or bilateral. It's kind of like a mental filing cabinet for engineering. But honestly, the most fundamental division you need to understand is between active and passive elements. Active elements, like your voltage sources or current sources, are the energetic heart of the circuit. They're the ones actually supplying the energy.
Passive elements, on the other hand, do not supply energy. They are the components that absorb, dissipate, or store that flow. If it helps, think of active elements as the engine of a car and the passive elements as your brakes and suspension.
For example, simple tools like resistors, inductors, and capacitors are categorized as passive elements. A resistor dissipates energy, while inductors and capacitors store it up. These are the roads and the speed bumps in our circuit. We also have unilateral elements, like diodes, where current only flows happily in one single direction. Compare that to bilateral elements, like resistors, which really don't care which way the current flows. It's just a beautifully organized system when you break it down.
And that brings us to our final section, Section 4, the rules of flow, governing laws of the circuit.
Okay, let's calmly map out our circuit. Before we apply any intimidating equations, we just locate its nodes, which are simply the junctions where two or more branches meet. Then we identify the branches themselves, which are the direct paths for the current traveling between those nodes. And finally, we look for closed paths, or loops, that start and end at the exact same point. By simply drawing this out, what looks like a terrifying diagram instantly becomes a manageable map of city streets. Once we have our map, we apply the foundational rule, Ohm's law. It states that at a constant temperature, the current passing through a conductor is directly proportional to the voltage across it. V equals I times R. Honestly, Ohm's law is the most elegant, simple rule of flow out there. It just means the pressure you need equals the flow you want multiplied by the resistance it meets along the way. Now, what happens when those flows crash into each other at a junction? That's where we apply Kirchhoff's current law. Think about the currents entering and leaving a central node. The absolutely crucial point here is that the algebraic sum of the currents meeting at a node is equal to 0. In simpler terms, whatever water flows into a junction must perfectly equal whatever water flows out. 0 energy is magically created and 0 is lost. It is always perfectly balanced. Similarly, we have Kirchhoff's voltage law, or KVL, for our loops. This rule demonstrates that if you walk in a complete, closed loop around a circuit, the algebraic sum of the voltages must be 0. The total voltage you gain from your active sources will exactly match the voltage dropped across your passive components. It's exactly like hiking up a mountain and coming back down to your car. Your net elevation change at the end of the hike is always 0.
So the next time you're faced with a dense engineering diagram, just take a deep breath. It really is just a logical system of pushes, flows, and simple rules. Active sources push the charge, passive elements guide it, and mathematical harmony dictates that everything balances out perfectly in the end. The practical takeaway here? Any complex system can be understood if you just follow the flow, one node at a time. Thanks so much for joining me on this journey, and I'll see you in the next explainer. What complex system will you decode next?